Welcome to our Chapter 7 lecture. Chapter 7 is titled, What's the Attraction? And the attractions that we're talking about are attractions between molecules. So we've talked a lot about um, chemical bonds like ionic bonds and covalent bonds, and these are the things that hold atoms together. But now we want to talk about the things that hold individual molecules together, like what holds all of the water molecules together in a drop of water. If you put a drop of water on the table, it actually fights gravity. There are some really strong attractive forces involved there that have a lot of energy, enough energy to fight the force of gravity. So those are the attractions that we're going to talk about. So we're going to talk about the different types of attractions. We're going to relate those to the different types of attractions that are present in biological molecules. So we have three major types of attractive forces that we're going to discuss in today's chapter, and we'll discuss those first, give a definition of the different types of attractive forces, and list them from the weakest to the strongest. And then we're going to talk about gases, which is a state in which we don't really have many attractive forces. You have very limited attractive forces. And then the attractive forces become stronger in things that are liquids and solids at room temperature. So we'll relate those types of attractive forces that we discussed to our different states. So our gaseous state, our liquid state, our solid state, what kind of forces are involved in these different states. We're also going to discuss attractive forces and how they affect solubility. We're going to find that like things dissolve like. So things that have one type of attractive force are going to dissolve other things that share that type of attractive force. And so that's why like oil and water don't mix. We're going to learn that that's because they have two different types of attractive forces. We're going to talk about dietary lipids and attractive forces in the cell membrane. We're going to talk about the attractive forces that are present in our lipid bilayer across our cell, and those are also the same types of attractive forces that are present in dietary lipids. So the first type of force that we're going to discuss is the London force. The London force is the weakest of the forces that we're going to discuss, and it's an attractive force that occurs when electrons become unevenly distributed over a molecule's surface. So in layman's terms, what's happening is these London forces occur in our nonpolar molecules. So they're going to be the dominating force in our nonpolar molecules. So in biological terms, those are going to be our hydrocarbons. So our molecules that have a lot of carbon and hydrogen in them. So particularly our fats. And fats also make up the lipid bilayer of the cell. So these are going to be the dominating force involved in holding hydrocarbons together. So those alkanes, alkenes, things along those lines that we looked at earlier. So what happens in a London force is normally between a carbon to carbon bond or a carbon to hydrogen bond, the electrons in the bond are evenly shared. They have an equal chance to be on one side of the molecule as to be on the other side. But because they're constantly moving back and forth, sometimes just by chance, just by a roll of the dice, they all happen to be on one side or the other, or more of them happen to be on one side than the other. When this happens, they generate a temporary pole. So there's like a temporary charge. And that temporary charge can affect the molecule next door and induce the opposite charge to happen. So because the electrons move over there, it pushes the electrons on the opposite molecule away. And so you end up with this charge-charge interaction. So this is an example of that. So you can have, and on the left here, we're showing you've got an even distribution of the electrons here. The electrons are all evenly shared. And then by chance, they happen to line up. So they all move to one side of the molecule. When that happens, you get a partial negative charge over here and a partial positive charge over here. And if this is one molecule, it can influence the molecules surrounding it and induce a temporary partial charge. So these are really transient interactions. Transient means short-lived. So these don't last for very long. So this is the weakest of the attractive forces that we have. A great example of this is like cling wrap. So it's not really difficult to pull cling wrap away from itself, right? So that's a perfect example of this type of attractive force. So this attractive force is responsible for holding fats together. This is one of the reasons why, like if you take butter, butter is not so hard to get the change from like the solid state to the liquid state. If you just hold it in your hand, it'll start to melt. So the attractive force that holds solid fats together is a pretty weak attractive force. It doesn't take a whole lot of energy to start to get that attractive force to break. So it's these attractive forces that hold molecules together, and this is the weakest of them. So we'll see that a lot of our hydrocarbons are going to be very weakly held together. So the next type of attractive force we're going to discuss is a step up from the London force in terms of strength. It's a little bit of a stronger interaction, and it's called the dipole-dipole interaction. So you've got a polar molecule, in this case, interacting with another polar molecule. So these molecules already have a permanent dipole because one of the atoms involved is more electronegative than the other. So let's go take a look at some molecules that exhibit this property so you can see kind of how that works. So we know that oxygen is more electronegative than carbon. So if we were going to draw where the electrons go, remember we use this kind of cross and arrow looking thing here. So the electrons are moving towards, they're getting hogged by the oxygen. They're getting pulled in the direction of the oxygen here. So we've got a partial negative charge up by the oxygen and a partial positive charge down here by the carbons. And so what's going to happen is this molecule, each one of these molecules has a permanent dipole where the electrons are always unequally shared on one side versus the other. And so these guys can link up like this, and this interaction doesn't break spontaneously. This just exists for a long time. And so these guys are held together a lot more strongly than with the London dispersion. Because we said that London dispersion is like a temporary dipole. It just happens for a second because the electrons happen to be on that side. And here, the electrons are kind of more so stuck to the oxygen than they are to the carbon and hydrogen for a longer period of time, or more on a more regular basis than what was happening in the London dispersion. So this is a much stronger interaction. So as far as biological molecules are concerned, you can see this. We've got ethers here as an example. So this is dimethyl ether, but this would happen in diethyl ether as well, which was used medically. And you can see this in a lot of your ketones as well, where you have that carbonyl group. So we have that C double bonded to oxygen. Any of these, you're going to have that partial negative up here by the oxygen and a partial positive down here by the carbon. And so you can get these types of attractive forces in those molecules. So the next type of interaction we're going to talk about is our third and final type of interaction is going to be the hydrogen bond. The hydrogen bond obviously involves hydrogen, particularly polarized hydrogen. Hydrogen is the smallest atom on the periodic table of the elements, so it's the smallest element. It only has one proton and one electron. And that one lonely little proton really doesn't do a very good job of holding on to that single electron. It just doesn't have a whole lot of pull there. A larger nucleus with multiple protons would do a lot better at holding on to multiple electrons. So when you have a polar bond between hydrogen and a very electronegative atom, the electron is really, really not shared equally. So oxygen, for example, when we talked earlier about the carbon to oxygen bond, how we showed a partial negative charge, this would be a really big partial negative over here. That oxygen can really pull that electron in his direction. So this would be a really big partial positive here. So the three most electronegative elements that we see commonly are oxygen, nitrogen, and fluorine. So oxygen, nitrogen, and fluorine can also be involved in hydrogen bonding. So in order for a hydrogen bond to occur, you have to have a really electronegative element, oxygen, nitrogen, or fluorine, bound to a hydrogen. So they are creating this really uneven dipole with big partial positives and big partial negatives. So you got to have a hydrogen bound to oxygen, nitrogen, or fluorine. And that's going to be what we call the hydrogen bond donor. It's going to donate the hydrogen. Our hydrogen bond acceptor then has to be a molecule containing oxygen, nitrogen, or fluorine with an available lone pair of electrons. So one of these guys, let's say oxygen, he's got two lone pairs. If you've got another oxygen with a hydrogen, that hydrogen has a big partial positive charge. So the electrons in this oxygen are going to be really attracted to that because they're negatively charged. So this oxygen's probably hogging the electrons from somebody else that he's bound to as well. So he's already got a partial negative charge to him as well. So it's like a dipole-dipole interaction, but it's even stronger. In fact, it's almost as strong as a covalent bond. This is the interaction that holds water molecules together. This is so strong that this force can fight the force of gravity. So these are some different examples of hydrogen bonds occurring. So this is an intramolecular. That means happening within the same molecule. So this isn't even between two different molecules. This is happening within the same molecule. You've got an oxygen with a covalent bond to hydrogen. Remember, that was one of our three guys we were looking for. You need hydrogen, and that hydrogen has to be bound to oxygen, nitrogen, or fluorine in order for this to be a hydrogen bond. So you've got that oxygen and hydrogen, and you've got another oxygen with a lone pair of electrons available to interact with our partially positively charged hydrogen. So this area right here, that's our hydrogen bond. Up here we're showing our hydrogen bonds in the dashed line. You can see each one of these water molecules is able to act as a hydrogen donor. So a hydrogen bond donor. The oxygen in water could also act as a hydrogen bond acceptor because it has free lone pairs. They're not showing that right now, but that can happen as well. So we've got this water acting as the donor, the hydrogen donor, and you've got the oxygen from this carbonyl. He has two lone pairs, so he can interact twice. So you can have two hydrogen bonds here with this guy. Now, I want to point out that while this big molecule right here, which is a ketone, this is 2-propanone is what they call this, because you've got the ketone on the second carbon. So it's propane with a ketone, so they call it 2-propanone. And this particular molecule has a carbonyl group in the middle. You've got hydrogens on it. So he can act as a carbon bond, or as a hydrogen bond acceptor. He can accept the hydrogen in the hydrogen bond, but this molecule cannot act as a hydrogen bond donor. So he can't do what water is doing here. And the reason for that is he's got hydrogens, but they're not bound to oxygen. They're bound to carbon. So if you only had this molecule, if you only had the 2-propanone and not water, 2-propanone would react with other molecules of 2-propanone through a dipole-dipole interaction. You'd still have a dipole at the carbonyl, but it wouldn't be able to do hydrogen bonding because it doesn't have a hydrogen that's attached to carbon. So that's a distinction I want to point out. We'll point out more examples of that when we do the problem-solving sections together here. So the next one we have here is ethanol. This is ethanol interacting with water molecules. So ethanol can act as both a hydrogen bond donor and acceptor. That's our ethanol right there. You can see he's got an alcohol with available lone pairs, so he can act as the hydrogen bond acceptor. That alcohol is, or that oxygen with the lone pairs is also bound to a hydrogen via a covalent bond. So he can act as a hydrogen bond donor as well. So each molecule of ethanol can be involved in 3 hydrogen bonds. The oxygen can be an acceptor twice because he has 2 lone pairs, and the hydrogen can be donated to another water molecule or to another molecule of ethanol as well. And this is one of the reasons why ethanol is what we call miscible with water. You can mix ethanol and water together at any concentration. They're perfectly soluble in one another. So this is one of the reasons why we can make a mixed drink with any strength of alcohol that we can get our hands on. These guys also bind together so tightly that it's difficult to purify them, to get them away from one another, because they have really strong interactions. So we have to distill them. That's a very costly method of getting these two guys apart or concentrating ethanol from water. We do have one more type to discuss. I had mentioned that there were three major types. This one's kind of similar. I kind of relate it back to the dipole-dipole. This is the ion-dipole interaction. So in an ion-dipole interaction, you have an ion, something with a full-blown charge, interacting with something with a partial charge. So that would be your ion-dipole attraction. So this is a very strong attraction as well, and it's essentially the attraction between like water and sodium, or water with chloride. This is the reason why we add salt to our roads. This interaction is very strong. So if you add salt to ice, it's going to break up the interaction between the water molecules that are frozen together. So it'll break up that interaction and actually turn solid water back into liquid water because it's breaking the forces that are holding the water molecules together. So this is a stronger force than the hydrogen bonding force we were just discussing, and that's why you can add salt to your ice on your roads and get the ice to melt, because this creates a stronger force than you've got salt water, which has a lower freezing point. You have to get that colder to freeze than if you had just pure water. Ionic attractions are very similar to just ionic bonds. We talked about ionic bonds earlier, and so in an ionic attraction, you've got two ions now, and they form what we call a salt bridge. So you've just got two things, with one with a fully negative charge and one with a fully positive charge, and those two things are just going to interact with one another. So this is an ionic bond for all intents and purposes. This is a very strong interaction. So we'll see salt bridges happen a lot in proteins. So we're going to see these groups called carboxylic acids, and they can take on a negative charge. We saw our carboxylic acids earlier as still having the H on them with this OH, and then you had the carbonyl here. And so that can lose this hydrogen, as we're going to learn in our acid-base chapter. And then amines can do the opposite. We're used to seeing amines as like nitrogen with 3 bonds and a lone pair. So that lone pair can be used to pick up an H plus or a proton. That gives us nitrogen, an extra hydrogen, and a positive charge. So that forms like ammonium. This is the ion of our amine groups. So the positively charged ion of our amine groups. And so these two can interact together, what we call an ionic bond or a salt bridge. So you might have an amino acid with an amine on it, an amino acid with a carboxylic acid on it, and these two can interact, and that will hold a protein together in a particular shape. So this is just a really easy table to determine what kind of bond you're working with. So you look at first, is the compound polar? If the compound's not polar, then you've got London attraction forces. So if you're working with a nonpolar compound, London force. If the compound is polar, then you have other possibilities. So we're going to look and see, is hydrogen bonding possible? And if hydrogen bonding is not possible, then we probably got a dipole-dipole interaction going on. The thing I don't like about this table is it should also give you an option: is hydrogen bonding possible, and are there ions present? Because you might also have an ion-dipole thing going on. So it should give you both of those options. But just be aware of that. So if you see that hydrogen bonding is not possible, you either have dipole-dipole or maybe ion-dipole. So we gotta look into that possibility as well. So if you do have the possibility of hydrogen bonding, so you've got an oxygen bound to hydrogen, or a nitrogen bound to hydrogen, or fluorine bound to hydrogen, and you've got another oxygen, fluorine, or nitrogen with a lone pair, then you've got hydrogen bonding. If you've got an ion present, then you could have an ion dipole or full-on ionic as well. So we discussed these attractive forces are what keep our biological molecules in the shape that they are. So these attractive forces are used to hold our biological molecules together. We talked about the London forces are going to be involved in the fats, holding fats together. So we'll see that the London forces are really involved in the lipid bilayer, those long hydrocarbon chains in the lipid bilayer. They're going to hold those things together. Cellulose molecules are held tightly together through hydrogen bonding. Remember, cellulose was one of our sugars. It had a lot of those hydroxyl groups on it. The hydroxyl group is O bound to H. So that can act as both a hydrogen bond donor and a hydrogen bond acceptor. So anything that looks like water, I like to say, if it's got an OH on it, like water is H2O, it's got an oxygen with two H's sticking off of it. Or if you just have that O with a single H sticking off of it, that's possibly going to be involved in hydrogen bonding. If you have HF, like hydrogen bond to fluorine, possibly hydrogen bonding. If you have NH, again, possible hydrogen bonding going on there. Hydrogen bonding hold our DNA double helix together in the twist. So we're going to see when we look at DNA in our future chapter, I think it's chapter 11 that we discuss DNA, we're going to see that the base pairs are held together by hydrogen bonds. Proteins are held together by a combination of all of these different attractive forces. So it can be dipole-dipole, it can be London dispersion, and many proteins are going to have all those different types of interactions going on at different parts of the molecule because proteins are just these large, complex structures. Now we're going to move on to the part of the chapter where we discuss how attractive forces affect the state that molecules are going to be in, or a material is going to be in. And I was going to skip over this for the sake of time, but I really want to go into it from the standpoint, especially for the gases. And some of these gas laws that we're going to discuss, you might think, well, this doesn't really apply to me if I want to be like a nursing person or if I want to get in the medical field. But it really does because you're going to be working with gases. So most likely you're going to have to put somebody on oxygen at some point in time. And so you kind of have to understand the properties of gas and how a gas can behave. So when we talk about gas, one of the things that's really important to discuss is pressure. So when we try to discuss the concept of pressure, I want you to imagine an empty syringe. So if you've got an empty syringe, if the plunger of the syringe is drawn all the way out, it's going to fill up with air. Unless you've got the end closed off, and then you're just creating a vacuum. So if we close the tip of that syringe and depress it, let's say we've closed it off now, we're squeezing that sample of air. So what we've done is we're increasing the pressure. The particles of a gas, they're usually very far apart from one another. If you look at if you took a sample of the air around you, the gas molecules are all very far apart from one another and they're bouncing around very quickly. They're moving around. They don't interact with one another for very long. They just hit each other, bump, and bounce off of each other. As we depress that plunger, we're compressing the gas. We're applying a pressure to it. So pressure is the force exerted against a given area. And it corresponds to the force that those molecules are also pushing back or putting back onto that container. So these molecules or atoms are moving really, really fast. And they do hit the side of that container. And even though they're very small, there are many of them. So pressure, like the pressure in our car tires, is enough to keep our cars even lifted up off the ground. And that's just the force of gases hitting the inside of your tire. So that's a lot of energy, going on in our gases. We as human beings have a lot of different units that we use for pressure. In this class, we're going to stick to atmospheres. The reason we stick to atmospheres is it's really simple. The pressure of our atmosphere is 1 at sea level. As you go up, the pressure goes down a little bit. So you're going to be close to like 0.99 something. So there are other different units that are used. There's the Pascal. We're not going to use that. There's the PSI or pounds per square inch, and there's also millimeters of mercury. You'll sometimes see that. Millimeters of mercury you'll use when measuring blood pressure. And millimeters of mercury is still used today because mercury was a really easy metal to measure pressure with because it's a liquid metal. And as the pressure in a room went up, the liquid metal would go up in a capillary. And it was really reliable, easy way to measure a change in pressure historically. So a lot of our early medical texts were written using the standard millimeters of mercury. And we've moved on as chemists, we use the atmosphere a lot, but we still use millimeters of mercury in a medical sense when we're talking about pressure, especially like blood pressure. So just be aware of that. It's a different unit than what we're going to discuss when we're talking about our gases. So this is an example of what I was discussing with mercury. This is like an early barometer. This is what you would measure air pressure with. So they'd have a little pool of liquid mercury. We don't do this anymore because we know liquid mercury is really toxic. It's a liquid metal. It's a toxic heavy metal. And those vapors from that liquid mercury can get into the air that you are breathing, and you've just inhaled a toxic heavy metal. So we don't really use these anymore, but we're still working with that millimeters of mercury measurement method, or that particular unit. So they would take a tube with a vacuum and it would suck up this mercury, but the mercury is also heavy, so it wouldn't go the whole way up in this tube with a vacuum. And as the pressure would increase on the outside, that would push down on the pool of mercury and push more mercury up the tube. So the mercury would rise in a very reliable way, and you would be able to figure out what the pressure was outside of the tube. So we've got 4 gas laws that we're going to discuss. There's really 3 gas laws, and then we're going to combine them into a final gas law. And the only one you'll be responsible for doing any math with is the final gas law that we'll discuss. So the first one is called Boyle's law, and it's the relationship between pressure and volume. And all it says is that if you cut the volume in half, you've just doubled the pressure. So they're inversely related. So the lower the volume, the more pressure you have. And this is the example. If we start with a given amount of gas, and this would be at 1 atmosphere of pressure, if we cut the amount of space in half, you have twice the pressure now. Those molecules are banging against the wall twice as often because they have less room. They have half the space to bounce around in. So you've just doubled the pressure. If you cut that in half again, you've tripled the pressure. So they are inversely proportional to one another. So our formula for that is P1 V1 equals P2 V2. That's how I was used to saying it instead of this IIFF thing, where it can be P initial, V initial equals P final, V final. So your starting pressure and your starting volume multiplied together are equal to the final pressure times the final volume. This is an inverse relationship because in order for this to be true, if we increase one of these, we're going to have to decrease the other one to keep these two things equal to one another. So as one goes up, the other one has to go down. So that's mathematically what an inverse relationship looks like. Boyle's law is really important biologically. It's very important for breathing. So Boyle's law, breathing is a direct application of Boyle's law. When you breathe in, the volume in your chest increases. So that means the pressure decreases. So as you open up your lungs, there's less pressure inside of your lungs now. So the pressure of the air on the outside of your body hasn't changed. So it's going to be higher now than the pressure inside. That's going to force air into your lungs. So when you expand your lung, that lowers the pressure, and the air, the higher pressure air outside of your lungs rushes in to fill that void. It's just like creating a vacuum. So you open that up and the air is going to rush inside. When those muscles relax, the volume of your chest cavity decreases. You've just increased the pressure in your lungs. Now that air is going to come out. It's going to bounce around in there faster and faster. It's going to try to get out to the lower pressure area outside of your lungs. Our second gas law is Charles' law. And this states that if you don't change the pressure or the amount of gas, if you don't allow those two things to change, the volume of the gas is directly proportional to its absolute temperature. We're going to talk about absolute temperature. This is going to be in the scale of Kelvin. So we had Fahrenheit, Celsius, and Kelvin were our 3 temperature scales. So you have to do this math in Kelvin. And that's because Kelvin has a number called absolute zero. When you hit 0 Kelvin, that's as cold as any material can get. And so this gas law works very well with Kelvin. It doesn't work so well with Celsius and Fahrenheit. You'd have to have some conversion factor involved there to make this math work. So when we work with temperature in the gas laws, we're working with Kelvin. So just be aware of that. So what happens is if you double the temperature of something and it's in a container that can easily expand, the volume is going to double if the pressure isn't changed. So if you're in a, and we're going to see in a second, temperature and pressure can be related too. But we're assuming that we're in a very flexible container, and so the volume is going to change and the pressure isn't. So as you double the temperature, you double the volume. If you make it colder, if you cut the temperature in half, you'll cut the volume in half. So the gas will shrink. So if things get colder, they shrink. They get hotter, they expand. That's really it for Charles' law. And you can see mathematically, it's the opposite of what we saw earlier because this is a direct this is a proportional, not a inverse reaction. So in order to keep these two guys equal to one another, if one of them goes up, the other one has to go up as well. So if you had, for example, 1 over 1 equals 1 over 1, both sides are equal to 1, right? So if I increased VF to 2, I would have to increase TF to 2 as well to make it still equal to 1. So as one goes up, the other has to go up the same amount. So the next one is temperature and pressure. So let's imagine you're in like a really rigid container. Let's say you're in a gas cylinder, like a big metal cylinder, and the volume cannot change. That cylinder will not expand at all. So this is the Guy-Lussac's law. It states that when the temperature increases, the gas particles move faster, hit the walls of their container more frequently, and this increases the pressure. So as the temperature goes up, the pressure goes up. And this also is a direct relationship. Okay, so this is a proportional relationship. So if you double the pressure, or sorry, if you double the temperature, you're also going to double the pressure. So again, just like we were saying earlier, if these both sides were equal to 1, I have my P initial over T initial was 1 over 1. If I increased my final temperature to 2, my final pressure is also going to go up to 2 in order to keep this equal sign true. So this is what happens in reality. So this is one of the reasons why in a fire, if there is a fire and they have gas cylinders in the building, that can become a very dangerous situation, especially depending on what gas is in those cylinders, because the pressure of those cylinders can go up and those things can go off like a rocket. They're already under very high pressure to begin with. As you increase the temperature there, you can really get a high pressure situation, and those things can shoot through a concrete wall pretty readily. And if you have a flammable gas in there, you're really going to be in trouble. So the final gas law is the combined gas law, and it just combines all of these gas laws together. So that's all it is. We've combined Charles' law, Boyle's law, and the Guy-Lussac law. So you've got PI VI over TI equals PF VF over TF. And if I gave you a problem to solve this, all that you would have to do is take, I would give you 5 of the 6 of these, and you'd have to solve for the one that I didn't give you. So it's just a little bit of mathematical rearrangement. So I might say solve for VF. If PI is this and VI is this and TI is this, and then you change something and PF goes up and TF stays the same, what's VF? It's just a little matter of substitution, which is easy math you guys should be able to do pretty easily at this point. So we'll do some examples of that in our problem solving sessions together in class. So we have another gas law that we're going to kind of skip over in this class, but I just wanted to mention it, and that's the ideal gas law. This is PV equals nRT, and this is used by chemists to describe, you can calculate the number of moles of a gas in a particular container if you know the pressure, the volume, and the temperature. That's not something that's going to be very applicable to the medical field, but I just wanted to mention it because we're talking about gas laws. This is an important gas law in chemistry. So all of these laws that we just discussed are gas laws, and these only apply to gases, things in the gaseous state. So they don't apply to liquids and solids. So now we're going to talk about how attractive forces relate to changes of state. These changes of state include freezing and melting, which are changes, of course, between liquids and solids, evaporation and condensation, which is between liquids and a gas, and sublimation and deposition, which is between a solid and a gas. So there are just a few. You might not be as familiar with the last set there, the sublimation and deposition, but there are a few materials that transition state straight from a solid to a gas at atmospheric pressure. And a great example of that is dry ice, or CO2. So at atmospheric pressure, CO2 transitions straight from a gas to a solid, vice versa, depending on the temperature. So dry ice is solid CO2, and as that melts or evaporates, it doesn't melt, it evaporates or sublimates straight into a gas. So these changes in state are, and when they happen, are related to the types of attractive forces that are held between the molecules. So essentially, as a substance is heated, the particles are going to begin to move faster. As you're adding heat, you're adding kinetic energy to the particles. And when I say particles, I mean molecules, atoms, whatever the substance is made of. So those particles are going to begin to move faster. And the text of the book here says, and the interactions between them become less important. That's not necessarily the way I view it. And the way I like to look at it is the kinetic energy overwhelms the attractive forces, you're going to break the attractive forces. So as you continue to heat a substance, you're adding more and more kinetic energy to those molecules. So there's a lot of energy in those bonds. As we talked about with water in that hydrogen bond, there's a lot of energy holding those water molecules together. Enough energy in those hydrogen bonds for the water to fight gravity and form like a droplet that fights gravity. So you have to add a lot of kinetic energy in the form of heat to that substance to get those water molecules to stop interacting with one another and break up and turn into a gas. And this is one of the reasons why water is such a great heat sink, why we can use water for like firefighting and things along those lines. It takes a lot of energy to induce a transition state in water. It takes a lot of energy to get ice to melt, and it takes a lot more energy to get water to boil or evaporate. And then substances that have weaker interactions, like our hydrocarbons that have the London dispersion force interactions or our London force interactions, those are going to require less heat or less energy to break their forces, to get them to go from one state to another state. So I gave the example of butter. It doesn't take a whole lot of time or energy to melt butter compared to melting ice. So this is just an example of the changes in states that we were discussing there. If you see the red arrows are state changes that require energy. So these are going to be endothermic state changes. So you're going to be adding energy in this case. If you're going from solid to liquid, it requires energy to break some of the attractive forces to go from a solid to a liquid. In a liquid, you still have attractive forces, but they're more transient. So liquids are fluid. The molecules aren't completely locked in space as they are in a solid. And then as we continue to heat the material, you're going to have vaporization, and that's going to be going from a liquid to a gaseous state. And as I said, some materials do the sublimation thing, where you go straight from a solid to a gas. We all know that if you leave a glass of water out, eventually that water is going to slowly evaporate, especially if you leave it out on like a hot sunny day or something along those lines. Or any gas, some liquids will evaporate faster than others. Like if you were to leave a little bit of, say, nail polish remover, acetone or something along those lines out in a little glass, it would evaporate. And the reason for this is the kinetic energy of the molecules in the liquid are not all the same. So some molecules are moving faster than others. And if two molecules bump into one another and they give enough kinetic energy, they can pop out of the liquid phase. If they're sitting right on that barrier between the liquid and the gaseous phase, if they're right on the edge and something bumps into them with enough force, they can pop them out into the gaseous state. And so you get a little bit of vapor that will build up above any liquid. So at a given temperature, the pressure above a liquid in a closed container is called the vapor pressure of that liquid. So the vapor pressure will change depending on the temperature. So if we increase the temperature, our pressure will also increase. And the reason for that is that these water molecules are going to start to move faster, whatever the liquid is. The molecules in the liquid state are going to start to move faster. As they start to move faster, more and more of them are going to break out into the gaseous state. Now, eventually you'll hit a state where you reach equilibrium, where for every one that pops out, another one goes back in. And it's at that equilibrium that you would measure your vapor pressure. It doesn't take very long for that equilibrium to be reached. But for every molecule that pops out, you have a molecule popping back in. And at that point, we're what we call equilibrium, where there's just going to be a constant concentration of gas molecules in the gaseous phase above that liquid. The boiling point then is related to our vapor pressure. The boiling point is the temperature at which the vapor pressure of a liquid equals the atmospheric pressure. Once you've heated something to the point where the vapor pressure equals the atmospheric pressure, that material will start to boil. It'll start to. So once they start to boil, what's actually happening is that those liquid molecules have gained enough kinetic energy to overcome their attractive forces to other molecules in that liquid. So the kinetic energy is overcoming the energy involved in those attractive forces, or those hydrogen bonds, or those dipole-dipole interactions, or London dispersion forces, whatever they are. So when you reach that boiling point, the molecules have enough energy to change from a liquid into a gas at that point. So we can predict what the vapor pressure and boiling point of one molecule is by just looking at the types of attractive forces. So just by looking at the structure of a molecule, we can determine which one's going to have the higher boiling point, which one's going to require more energy. The more energy that's required to break those bonds, the higher your boiling point is going to have to be. So stronger attractive forces are going to predict for higher boiling points. So if we had to go from lower boiling point to higher boiling point, we'd start with our London dispersion forces. So those are weak interactions, so they're going to have low boiling points. And our dipole-dipole are going to have slightly higher boiling points than those. And then our hydrogen bonding interactions are going to have higher boiling points. And then our ion dipole are going to have higher boiling points. And then our ion-ion really are going to have the highest boiling points there. We can even take a look at molecules that have the same types of attractive forces and make some predictions. So London attraction forces occur between molecules, and they occur along the surface area of those molecules. So for example, pentane versus octane, pentane's got a smaller surface area than octane does. So we've got our pentane shown here, and we've got octane here. So they've got 5 carbons versus 8 carbons. We've just got a longer molecule for octane. So there's more surface area for our octane, therefore there's more of those London force interactions. So who's going to have the higher boiling point? Pentane or octane? Remember, the ones with the higher boiling points require more energy to get to to boil. And that's going to be octane. And the same go for our melting points as well. So it requires more energy to get something to go from a solid to a liquid state as well. So these guys will have a higher melting point and boiling point as well at the same time. So this is a really great slide that represents what we were just discussing with the boiling point issue. So all of the first 4 gases here, methane through butane, or the first 4 molecules we're looking at, are gases. So these guys exist at gas at our normal room temperature. They have very low boiling points. So as soon as you get above the boiling point, you're now a gas. So because our room temperature is about 25 degrees Celsius, somewhere between the 22 to 25 range, depending on where you're at, These guys are all below that. So they're going to be in the gaseous state. These guys all have boiling points above our room temperature, so you would have to heat them somewhat. This guy, pentane, is pretty close to your body temperature, so you got to drop him on your body. It might start to evaporate pretty rapidly just from the heat from your body. Whereas you'd have to start to heat up hexane to get it to totally evaporate. Now that's not to say that these guys won't slowly evaporate if you leave them in a cup. Out in a cup, they'll still have a vapor pressure. There will still be some transition from the liquid to the gas state, but it won't be so rapid a transition that you've induced boiling. So the boiling point, again, is a measure of when the kinetic energy is equal to the energy in the attractive forces, when you start to actually see the physical bubbling. So these guys here, pentane, hexane, heptane, octane, these guys have those London dispersion forces, which are weak interactions. Our gasoline, mostly octane, and it's very fragrant. We can smell that gasoline as you're filling your car up. And one of the reasons is it's a very volatile liquid. It's still a liquid. It's still below its boiling point at room temperature when you're filling your car up, thank God. That's one of the reasons why we use this as a fuel. It's easy to transport because it's a liquid, but it evaporates very quickly. If you spill a little bit, it's going to evaporate and go into the atmosphere because it's this weak London interaction. Whereas you can leave a glass of water on your nightside stand and it could be months before that water is totally evaporated. Whereas if you left a glass of gasoline out on your nightside stand, beyond the fact that that might, suffocate you or create a flammable atmosphere, that stuff will have evaporated much faster than water. The shape of the molecule is also going to influence the vapor pressure and boiling point. So straight chain molecules with the same number of carbons in them are going to have higher boiling points than branched molecules. And the reason for this is it's easier to stack these guys together. It's easier to stack the linear molecules together than it is to stack these guys with branch points. They just don't fit together very well. So if you're trying to stack a whole bunch of straight logs versus if you're trying to stack a whole bunch of trees that still had their branches on them, the ones that stack up easier are going to have more contact between the two molecules, so there's more London dispersion forces. The more attractive forces, the more energy it takes to break them. Melting point, we see the same thing with melting point. Melting points follow the same trend as boiling points. The stronger and more numerous the attractive forces, the higher the melting point, the more energy it takes to melt that material. So attractive forces also control our solubility of materials. They determine what material is going to dissolve in what other material. So the golden rule of solubility is like dissolves like. Molecules that have similar polarity and participate in the same types of attractive forces will prefer to dissolve with one another. So they will have similar interactions and they will mix together very well. So things that have poles, strong polar parts of the molecule or dipoles, will want to do that dipole-dipole or hydrogen bonding possibly. They won't want to interact with other materials that have London dispersion forces. So this is why oil and water do not mix. Water is a polar molecule. It can interact through dipole-dipole or hydrogen bonding interactions or ion-dipole interactions. It can dissolve salts and things along those lines. Oil is very unlike that. It only has those London dispersion interactions. So the two will not mix together very well at all. In biological chemistry, your polar molecules are going to have functional groups like hydroxyl groups, that OH that's present in this molecule here. They could have amine groups, which has a nitrogen with those hydrogens. Remember, this was a polar bond, the nitrogen to hydrogen bond. They could have amine groups. The carbonyl, that's going to be a polar guy. And of course, if you've got an ion involved, as we have with our carboxylic acid in its conjugate base state here, where it's lost the hydrogen bound to the oxygen, that's going to be an ion dipole. So that's going to be a very polar compound. The same with our nitrogen if it picks up that fourth hydrogen, that fourth bond to give it the plus charge here. So our polar compounds are going to interact very well with one another. So things like our sugars are going to dissolve in water, and that's going to be part of like the cytosol. So our inside the cell, outside of the cell, that's going to contain all of our polar compounds. Ions can interact with water in a very similar fashion what we were just discussing. they can line up with the partially negative side of water or the partially positive side of water, depending on what ion you're talking about. If you're talking about an anion versus a cation. So if you've got the positively charged cation like sodium, sodium here is going to line up with the negatively charged oxygens, and chlorine is going to line up with the positively charged ions here. And they will associate with a particular number of water molecules around them. This process is called hydration. So because all of these oxygens only have a partial positive or partial negative charge, it takes more than one of them to hydrate that sodium ion. So you'll have several water molecules bump up against that sodium ion, and they will hydrate that sodium ion. And this is one of the reasons why we mentioned that if you add salt to ice, if we add road salt to ice, it's going to break up ice molecules, or these water molecules. They're going to stop interacting with one another, and they're going to start to interact with these sodium and chloride ions, because this is a stronger bond than the hydrogen bonding pairs that are typically involved in water. Now, we previously mentioned our polar molecules in biological substances. Now I want to give it a great example of a nonpolar molecule, and that's going to be one of our fats. So if you have a fat or a fatty acid, this is an example of a single fatty acid chain. You have this big, long hydrocarbon chain, and that is very nonpolar. So that section is going to be nonpolar, and they're going to want to interact with one another, and those chains are going to want to line up. In biological systems, we can have a lot of what is called an amphipathic compound. So an amphipathic compound is a compound that has both a polar and a nonpolar group. So a lot of our fats are just like this. They've got a polar head group. So here we've got a carboxylic acid. So this is just a simple fatty acid, single chain fatty acid. And you've got a polar head group, carboxylic acid. That's why we call it a fatty acid. It's got the hydrocarbon chains, which we associate with fats, and it's a carboxylic acid head group. So it's got an ionic head group and a nonpolar hydrocarbon tail. So what you will see is that the polar parts are all going to line up with one another and want to interact with one another. And the nonpolar parts are going to try to line up with one another. And this is going to give rise to structures like micelles that we use in our soaps. So this is an example of the one that we're showing here would be if you break down fat into the individual fatty acids, you've generated soap. So if you take and react like animal fat or vegetable oil with sodium hydroxide, you can break up these fatty acids that we have, or you can break up these two-tail, three-tail fats that are present in our oils and fats and generate these fatty acids, and this would be soap. So these guys can all line up in smaller particles called micelles. If you have your two-chain fatty acids, those can line up in what we call our cell wall, or lipid bilayer. So we said soap is one of our fatty acid salts. So most soaps that you buy, they're going to be like sodium and then some other sodium lauryl sulfate or something along those lines. So it's going to be sodium and then this amphipathic compound. It could be potassium or magnesium or calcium. There's going to have some counter ion, and then the amphipathic molecule, which is typically a negatively charged head group and a long fatty acid chain. You can have a positively charged head group and a long fatty acid chain as well. So they make different types. And so what happens is if we want a grease to dissolve in water, we just mentioned that oil and water doesn't mix very well. So we need an amphipathic compound. We need something that has both the properties of a fat and the properties of a polar compound like water. And this will be able to dissolve our greases in water, or get our greases to mix with water. It's not technically dissolved because they form these little micelles, or these little nano-sized droplets of fat inside these little bubbles of these amphipathic compounds. So what will happen is the fatty acid chain is going to interact with the grease or whatever you're trying to get off your frying pan. And then the positively charged head group is going to interact with the water on the outside. And that's going to break up that big blob of grease or whatever it is you're trying to clean off of whatever you're putting soap on. And it's going to make it appear to perfectly dissolve in water. It's going to mix with water in the form of these micelles. So the nonpolar part that we just discussed, that's called hydrophobic. It means it's water fearing. So that hydrocarbon shale is our hydrophobic region. The head group is our hydrophilic region. It's a hydrophile. It loves water. And then these tails, the hydrophobic tails, are going to associate with one another. That's going to create the core of what we call a spherical structure or a micelle. And the polar head groups will form the shell, and it's the polar head groups that will interact with the water, and the hydrocarbon shales that will interact with the grease that you're trying to dissolve. And this is just a picture of what we were discussing earlier. So this is an example of a micelle. So you've got your polar head group shown by the circle there. You've got your hydrocarbon chain, and if you had just a whole bunch of grease, which would just be hydrocarbon, that would interact, get stuck in the center here. So your grease can get taken up, mixed in with this stuff, and this will carry your grease away for you. So let's just take a look at these real quick and talk about which one is more water soluble. Which one do you think is more water soluble? So go ahead and pause it, think about that for just a second, and start it back up again when you have your answer. So if we look at the two molecules, when we're trying to determine which one's going to be more water soluble, I want you to look at things that look like water. Look for things that just look like water. And water's got an oxygen bound to two hydrogens. And so if we're just looking at this part of the water, I see that here, 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 here. I've got all these, and there's a polar group here, so that could interact. Another polar bond here. We got polar things going on all over here. This guy, I've only got these two regions, that might interact with this water. The rest of it got a big long hydrocarbon chain. This is an aromatic group here. So these are non-polar regions. So it's got a little polar head. This is an example of vitamin E, alpha tocopherol, and this is one of our fat-soluble vitamins. So they'll put this vitamin D and E will be in your milk. This is one of the reasons why if you drink whole milk, you actually get better vitamin absorption than if you drink skim milk or non-fat milk. So that's just because these are fat-soluble vitamins. You need that little bit of milk fat to absorb that vitamin. If you're not one of those unlucky lactose intolerant people, that can't handle milk or can only handle small quantities of milk, then you could get your vitamin E through a lot of there are other food sources for vitamin E as well. We just tend to use milk as a transport vehicle because in the form of whole milk, it provides very good vitamin absorption for vitamins D and E, which are both fat-soluble vitamins. So we've mentioned fats and we've mentioned oils, and we just want to give some distinction between the two. And really, it can be said in this one little title here, fats are solids. That's the difference between a fat and an oil. A fat is a solid, an oil is a liquid. An animal fat is a solid or semi-solid material. We say semi-solid because you can change its form by squishing it. So it does have some properties of a liquid, but it's for all intents and purposes a solid or semi-solid. It's typically a triglyceride, which means that it's going to have three fatty acid chains coming off of a glycerol molecule. So you've got three fatty acids joined to a glycerol backbone, and we'll show you a picture of that in a second here. So when the hydrocarbon chains, these tails of the fatty acids are saturated. We have this long straight chain hydrocarbons. This is a fat. If you add a lot of double bonds to that, we talked about how these double bonds, that's a poor drawing of that. Let me start up top here. These double bonds can induce a kink in the molecule. So they can make the molecule kind of change directions. So they induce a kink. And just like when we mentioned the straight chain hydrocarbons are going to stack together a lot better, and so they're going to be solid at higher temperatures, we have the same deal going on with our hydrocarbon chains and our fats. If you got these straight chain saturated hydrocarbons, they're going to have a higher boiling point or higher melting point, and they're going to be a solid at higher temperatures. And this is one of the reasons why they can cause artery blockage. So they can form a solid in your arteries, whereas our unsaturated fats are going to be less likely to do that. So glycerol is a molecule with 3 carbons in a chain, and it's got 3 alcohol groups on it. And I'm not going to draw all the rest of the hydrogens around those carbons, but each of those carbons has their octet met with covalent bonds to hydrogen. So what's happened is we've taken 3 carboxylic acids and we've made esters with these alcohol groups. So the carboxylic acid's lost an OH group. The alcohol here has lost its H, and we form a new ester. So this is a triester. So this is a triglyceride. It's got 3 fatty acids, and there's a glycerol molecule. There's the glycerol backbone right there. So here's your glycerol backbone. Here's all the, and we've got your 1, 2, 3 fatty acid chains coming off of that guy. So that's just what those look like in 3 dimensions. So what we're showing here is that the top one in A would be like an animal fat. This is mostly a saturated triglyceride, almost completely saturated. It's got 1 double bond in there. And then down here we've got the oil, where you've got like vegetable oil or olive oil, where this is going to exist in a liquid state because there are more kinks in the molecule. And as you can see down below, this guy down here wouldn't stack together as well as this guy up here would. So as we were discussing, fats are solids at room temperature, and the reason for this is they've got these long hydrocarbon tails that are restricted by London forces. And if you remember, our London forces were our weakest kinds of forces, but these fat molecules are pretty big, so they have a lot of them. And that's why these guys act as a solid. Number one, they're large molecules, so it's going to be harder to heat them up to the point where they're going to like evaporate, or even go into a liquid state. So it's going to take a little bit of energy to get them to go to a liquid state. Oils can be equally as long as fats, so they kind of have the potential to have just as many London dispersion forces, but they're these kinked up looking molecules. So these bent looking molecules, so they don't fit together very well. They don't have as many surface to surface contacts, so they have fewer London dispersion forces, and this is why they tend to act as a liquid at room temperature. The next molecule that we want to take a look at is going to be our phospholipids. These are very much so related to our triglycerides. Our triglycerides are how our bodies store energy in fats. So we're going to store as many long chain fatty acids on one molecule as we can. But from a structural standpoint, we're going to find that if you only have 2 of those fatty acids on a glycerol backbone, you can get a cool new structure, which is the lipid bilayer. So evolution has created the phospholipid. So we have this main structural component of our cell membrane, which is called a phospholipid. It's still got that glycerol backbone. It's going to have 2 fatty acids linked together through an ester, and that 3rd carbon is going to be bound to a phosphate containing group. Phosphate is a very polar ionic group. So it's got a phosphorus bound to 4 oxygens, and one of those 4 oxygens at least, depending on the pH, has a charge to it. It's typically going to have a -1 charge. You can have a wide variety of phospholipids depending on the different chains that you add to them. So we could have those 2 hydrocarbon chains. So you could have a very saturated hydrocarbon chain. You could have 1 saturated, 1 unsaturated. You could have 2 unsaturated, or you could have something in the middle where they're just partially saturated, partially unsaturated. And that can change the boiling point or the fluidity of the lipid bilayer. So you'll see that like organisms that live on thermophil or like heat vents at the bottom of the ocean are going to have these very saturated hydrocarbon chains in the phospholipids that make up their cell wall because they don't want their cell wall to melt. They're going to also have a lot of like cholesterol, things along those lines that are going to bind to that strongly with a lot of London dispersion forces and hold that together so that they don't melt. They're going to have these long chains and they're going to be saturated. Whereas things that live in more temperate or moderate climates might have a mixture so that we have a more fluid membrane at our increased or at our lower temperature here on the surface rather as compared to like a volcanic heat vent or something like that at the bottom of the ocean. So you've got these 2 tails, and also we can add things to that phospholipid head group, that polar head group, that could change the function of that phospholipid as well. So really a takeaway, or what I would expect you to know from a test, I would expect you to see something like this and know that it's a phospholipid. what you're looking for is you've got the two big long hydrocarbon tails. These are parts that you should be able to point out. The two fatty acid tails. There's your glycerol backbone. There's your phosphorus. So this must be your head group. So this is your polar head group. It's an polar ionic head group here. So that's the breakdown. What you ought to know about phospholipids. They've got the two tails, and we're used to seeing this particular structure drawn in our biology books where we show these guys lining up to form the lipid bilayer. So we looked at mice cells earlier, and the mice cells were just made of like single chain fatty acids. And if you notice, those didn't have a bilayer. Those just had like a polar group on the outside, and then everything on the inside was the hydrophobic region. And because we have that second fatty acid chain in there, these guys are going to line up to form more of a straight structure. It's not going to have as much of an angle to it, and that's what forms the cell membrane. So because we have that second hydrocarbon chain in there, instead of forming a monolayer, we now have to form a bilayer to get those hydrocarbon tails hidden from the water outside of the rest of those molecules as they're lining up. So our cell membrane forms a bilayer of phospholipids with the head groups facing in opposite directions and the tails all facing each other on the inside of the bilayer. And this, of course, is that classic representation that we're used to seeing in our biology books. We've got the aqueous environment outside of the cell, inside of the cell, and this is all our nonpolar region. So the body can add different things into this nonpolar region. We can have nonpolar parts of proteins, so we can get an intermembrane protein that spans the membrane, and these are going to be our proteins that are involved in allowing things to pass through. So let's say we've got to get calcium through. You'd have a calcium channel. If you had calcium 2+, this couldn't get through that membrane. So there are going to be other things inside of this that the body puts in there. So we're going to have channels for our different ions. We're going to have signaling proteins that can sense things on the outside of the cell and cause a change on the inside of the cell. So these become what looks like a very simple structure here. The bilayer is actually just a canvas or a region for many different potential. It's just a host for multiple different proteins that can have many different functions. So we just mentioned proteins can span these bilayers. They can be what we call an integral membrane protein, which associates with both surfaces, or a peripheral membrane protein, which only sticks out on one side of the surface. Most of these integral membrane proteins are going to be used to select molecules that can move inside and outside of the cell, so we can control what's inside and outside of our cell. We can control the interior environment and the exterior environment. All of our signaling is going to occur. Things are going to bind to the outside of the cell, and that might create a change on the inside of the cell. What we call this fluid mosaic model is we get these groups of proteins that can bind together in what we might call a lipid raft. And it's kind of like a small region, a protein-dense region of proteins that are spanning this lipid bilayer. So we call this the fluid mosaic structure. And the reason it's called the fluid mosaic structure is it looks like a mosaic, which is kind of like a pattern in tile. So it's a two-dimensional image, but it's fluid. So these proteins can't rotate within the plane of the lipid bilayer, but they're free to kind of dance around if they stay in their orientation. So for example, this guy here has to maintain that general vertical. He can't rotate like this inside that lipid bilayer. He's got a polar section here, a polar section here, and a non-polar section here. And so he's kind of stuck vertically in that lipid bilayer, but he can kind of move around the surface. So he can float around as long as he stays vertical. So that's why they call it the fluid mosaic model. So another group of nonpolar molecules are steroids, and cholesterol falls into that steroids group. So steroids contain these four-membered fused rings, and these are hydrocarbon rings. They can have other functional groups sticking off of them, and there's a wide variety of different places you can stick functional groups, and those give rise to our many different types of signaling molecules or steroids like testosterone and estrogen that influence sexual development, things along those lines. And additionally, cholesterol, shares a similar structure. So these are ring-like structures. They can have many different functions in the body, including emulsifying dietary fats, or again, they can be involved in hormone regulation and signaling. All right, so cholesterol is one of the steroids that we were discussing, and it has this polar head group here and this big long fatty acid chain here. And that can slip in between the hydrocarbon tails. In phospholipids, that can either increase fluidity, or in the presence of saturated hydrocarbon tails, or in the presence of unsaturated tails, it can increase the rigidity of the membrane. And so it can do one or the other depending on what type of hydrocarbon you're sticking it in. And so these can essentially modify how fluid your membrane is. So the body can increase or decrease this particular guy. And one of the reasons that cholesterol is, high blood cholesterol, not so good for you, for your heart anyway, is that it can bind to these saturated or unsaturated hydrocarbons and increase the rigidity of them and cause them to clog your arteries. So that's one of the reasons why they want to watch your fasting cholesterol levels. So that wraps up Chapter 7, major takeaways. You want to know the types of attractive forces and how to recognize them. You want to know about gases, that we don't really have many attractive forces that are just bumping against each other. Scrap the ideal gas law. You want to know this combined gas law and how to work with that combined gas law. Now, I want you to know the properties of these laws. You don't have to memorize the formulas for these laws or anything along those lines, but I want you to know get the general gist of them. So like if we change temperature, what happens to pressure? If we change pressure, what happens to volume? So get to know the cause and effect relationships between those laws. Understand the attractive forces in liquids and solids and how they affect boiling point and vapor pressure, and understand the attractive forces and how they affect solubility. And finally, we want to understand dietary lipids and the attractive forces between our different families of lipid molecules that we discussed and how those are involved in the cell membrane.